Hi everyone, Chris Tisdell here again. Thanks for tuning in. In this presentation, I'm going to continue my series on matrices and linear systems. And in particular, I'm going to discuss an example that connects span of vectors with these linear systems and matrices. So it kind of brings together a few different but related areas in a nice way. So let me share my screen with you and we can get down to business. Here is the example we are going to discuss. We've got a vector. We don't know what B1, B2, etc. are, but we're asked to find or determine the condition or conditions that this vector lies in the span of these three given vectors. Okay, so first we've got to understand what this question is trying to ask of us and then how to actually solve it, right? So in other videos, for example, my playlist on vectors, we talk about the span and linear combination of vectors. But mathematically, what's going on here? Okay, so if this is, say, the vector v1, this is the vector v2, and this is the vector v3, okay? What this question is asking you mathematically is, are there values of lambda 1, lambda 2, and lambda 3 such that, oh, let me move that over a bit, such that we can write this vector as a linear combination or linear combo of these three vectors. So basically it says that V is this. Okay. And let me just zoom out a bit more. All right, so mathematically, that's what the question is asking us. If we can find values of lambda 1, lambda 2, and lambda 3, such that this holds, then this does lie in the span of this. Now, there are also geometric interpretations of span. I'll leave those for my other videos. But how do we actually relate this back to matrices? Well, essentially, this is a vector equation, right? The unknowns are lambda 1, lambda 2, and lambda 3. We can write V1, V2, V3 as a matrix, and then this as the right-hand side or the right-hand column of our matrix, okay? So let's write that down, and this should be looking familiar now because I've done a lot of videos on this. So basically you have the coefficients, which in this case are just the columns here, and you have the right-hand side this, so, or I guess the left-hand side in this case. Okay, so 1, 3, 5, 5, 1, 4, 6, 7, 2, 3, 7, 4, and then this sort of plays the role of an equal sign, if you like. Then B1, B2, B3, and B4, which we don't know, okay? All right, so we have now successfully transformed our problem to an augmented matrix. What do we do now? Well, we want to talk about and delve into the solvability of this problem. So we do our row operations and put the augmented matrix in a row echelon form. And there's a definite procedure for that, which I have videos on, and I'll run you through it in this example too. Okay, so the first process is to choose a pivot entry or a pivot element. Now, 1 is a good choice because it's simple and it's already up in the top left-hand corner of the matrix. So I don't have to do any row operations to get that one up there. Now we turn our attention to everything underneath that one. And I want to make that a 0, that a 0, and that a 0. And I can do that through row operations. So row 2 will become row 2 minus 3 row 1. Row 3 will become row 3 minus 5 row 1. That'll become 0 then. And row 4 is going to become row 4 minus 5 times row 1. All right, so let's do those operations and see where it takes us. Okay, so I'm just going to list them here. So row 2 equals row 2 minus 3 row 1. Now I can do this, I can do 3 operations at once because they're all working on different rows, okay, with the same row 1. So row 3 equals row 3 minus 5 row 1. And we record the operations because it's easy to make a mistake. And if you make a mistake, you've got to backtrack and make sense of it. It's also good to show you're working. Okay, so let's do the operations now. So the top row, of course, is not going to change. All right, I'll draw this in a bit later. All right, so row 2 equals row 2 minus 3 row 1. So that'll be 0. 3 minus 3 times 1. 4 minus 3 times 1, 4 minus 1. 3 minus 3 times 2, 3 minus 6. That's going to be negative 3. And now B2 minus 3 times B1. Well, we don't know what B1 is, so it's just B2 minus 3 times B1. Okay, row 3 equals row 3 minus 5 row 1. That'll become 0. 6 minus 5 times 1, that's 1. 7 minus 5 times 2, that's negative 3. And B3 minus 5 times B1. And the last one, row 4 equals row 4 minus 5 row 1. So we'll get 0, 7 minus 5, which is 2, 4 minus 10, which is negative 6, and B4 minus 5 times B1. Okay? Okay, so that's the first step. Now we look at a submatrix and do the same thing with that. Okay? Let me show you what I mean. All right, so we've got all those to 0. Brilliant. So now we work on this submatrix. So we forget about these things. We want to choose a pivot entry. It's already a 1. It's already in the top left-hand corner. Brilliant. So then that's my pivot entry. And I want to get everything underneath that to a 0. So it'll be row 3 equals row 3 minus row 2. And row 4 equals row 4 minus 2 times row 2. Okay, so let's do those, and then we might be getting somewhere. Okay, so here we go. So row 3 equals row 3 minus row 2. That'll make that a 0. And row 4 equals row 4 minus 2 row 2. All right, so let's see if we'll work that out. So the top row is not going to change. The second row is not going to change. All right, so now this row 3 equals row 3 minus row 2. So we'll get 1 minus 1, negative 3 minus negative 3. So that's negative 3 plus 3. And then we get B3 minus B1 minus B2 plus 3B1. So we'll get the following. B3 minus 2B1 minus B2. And lastly, row 4 equals row 4 minus 2 row 2. So that'll be 0, 2 minus 2, 0. Negative 6 minus 2 times negative 3, negative 6 plus 6, 0. And B4 minus 5B1 minus 2 times B2 plus 6B1. So that'll be B4 minus 2B1, 2B2 plus B1. Okay, I've just squeezed it in there. Great. Okay, so a little bit tedious, but now we can look at our row echelon form and see what the conditions are on B1, B2, etc., for this system to be consistent, for this system to have one or more than one solution. Okay, so let's have a look at the format of our row echelon form now. Okay, so you'll see here that basically in other videos I've talked about the importance of this column being not leading. Okay, so we can the problem will be consistent if this column is not leading. So what I mean by leading is if I look along these two rows, basically I've got rows of 0. So this doesn't, this isn't 0 and this isn't 0. Why is that important? Because, well, basically, if this entry is not 0, what does row 3 say? It says that 0 lambda 1 plus 0 lambda 2 plus 0 lambda 3 equals something that's not 0. Obviously, that can't make sense. And the same for row 4. Okay, so in other words, for this to be consistent, we want that to be non-zero and that to be non-zero. Sorry, we want, sorry, let me say that. We want that to be 0 and we want that to be 0. Okay, then you've got a whole row of zeros and it's consistent. Okay, so we want this to be 0 and this to be 0. All right. In other words, if those two entries are 0, then the very left-hand column is what we call non-leading. Okay. All right. All right. So we want this to be 0 and this to be 0. So let's write that down then. Okay. So you can say that column 4 is non-leading when B3 minus 2B1 minus B2 equals 0, and when B4 minus 2B2 plus B1 equals 0. And in that case, all the other columns, well, that column's leading, that column's leading, that's not leading, but that's okay. All right. Hence, the system is consistent. Let's call that star. When B1, B4 satisfy star. Okay, what does that mean? Well, it means that the condition on these values here, the B1, the B2, the B3, B4, is these. Okay, for this to be in the span. Okay, so to answer the question, is condition star. Okay, that's it. Okay, so what do you think? It's a nice connection between vectors, linear systems, and matrices. Okay, now if you have any questions, any comments, I'd love to hear them. You can put them in the comments section. Hope you've enjoyed this series on linear systems and matrices. I'll be starting a fully dedicated playlist on matrices soon, so hope you can join me for those presentations. Thanks for watching, everyone. Bye.